All right, guys. A lot to do today. I'm a little sick, so hopefully my voice will carry us through. Should have been an in-class problem day. That would have been perfect, but alas, I'm talking at you the whole time. So solutions, we just had office hours. I'm bringing that, so the solutions are here. I actually have to run after class, but I will bring them again tomorrow, 2 to 2:30, and I'll just keep bringing them to office hours. So the grades are, as I explained on Piazza, there were some discrepancies, and I just wanted to make sure that everything was in order before we release them, so they'll be out in a few days. In the future, I expect that we can get them out in a week. And let's see, and next week, I am moving on Wednesday, so I won't be able to make it to office hours. Hopefully, I'll make it by class time. But yeah, so I'll have an office hour Thursday, 1:30 to 2:30. I could add some other times if there's demand. Just mention that in Piazza. Okay, so as we mentioned last time, here are the definitions of the class of problems P and NP. In both, the solution size that you're looking for should be polynomial and the input size. But in P, you need to solve the problem in polynomial time. For NP, you just need to be able to verify someone else's solution in polynomial time. And we'll see a lot of examples of these problems today. Right, and so we saw last time the SAT problem, which is sort of the first NP problem, first NP complete problem. And just to refresh your memory, here we're given some Boolean formula in conjunctive normal form, which means that we have ors within the clauses. So these underlined things are the clauses, and they're separated by ands. And the problem is, given some formula, decide whether or not there's some setting of true or false to all the variables that makes the formula true. And if not, output no. Okay. And as we saw last time, SAT is in NP, because if someone gives you an assignment of true, false to all the variables, you can just go through and just verify, yes, each clause has at least one thing that's true. Right, you can do that in linear time, super easy. So it's in NP because you can verify the solutions, but as we'll see, there's no known efficient algorithm to actually find a solution. So that's the Cook-Levin theorem, which doesn't, right, so we don't know whether P is equal to NP. So a corollary of that statement is that we don't know how to solve SAT. And the key theorem is the Cook-Levin theorem, which says that SAT is NP complete, meaning if you give me any problem in NP, if I can solve SAT efficiently, I could solve that problem efficiently. And what's amazing about this theorem is all you know about the problem is that it's in NP, meaning all you know about the problem is that there's some way to verify solutions to x in polynomial time. And somehow the theorem, it's a very fascinating theorem, that somehow just knowing that you can show that if you could solve SAT, you could solve all these problems. And the way it works is whatever program that you had to verify the solution, write it down as a Turing machine, and encode the fact that that machine is running according to the rules of Turing machines into SAT. And if it ran in polynomial time, then the SAT formula is only polynomial size and length, and et cetera, and you can show that if that's satisfiable, then that means there is a valid computation path of the Turing machine that arrives at a solution. So like I said last time, you don't need to know this theorem, but I would feel sad if you didn't know about it. Okay, but for what we need to know is that SAT is NP-complete. So meaning, given any problem in NP, if I could solve SAT, I could solve that problem. And what we're going to do today, the first part of today, is just going through a bunch of other reductions. So you could think of this as reducing X to SAT, meaning that I have this complicated problem X, but oh look, it's just SAT. The direction of what's being reduced to what is often confusing. Hopefully after a whole bunch of examples, it'll be clear. I know it won't be, but I can still hope. Okay, so the next thing we're going to do is reduce SAT to 3-SAT. So 3-SAT is a strictly simpler problem to SAT. It's SAT, but we have the extra restriction that the clauses have at most 3 literals. So this would be okay, this would be too big. So we need only 3 literals per clause. But what this reduction says is, hey, that's still just as hard. And here's how the reduction goes. Basically, for every clause like this that has too many variables, I'm going to introduce new variables y1 through y whatever. And I'm going to stick one, so I'll take the first 2, and then I'll add a y1, and then I'll continue on with the remainder, but I'll add a not y1 at the beginning. In general, like if I had an x5 or x5, then this would be not y1 or x3 or y2 and not y2 or x4 or x5. Right, so I'm just using these variables to kind of glue together. And you can see that, okay, the first thing I need to check, I should not be adding too many extra variables here. So for any clause, basically the length of any clause is a bound on how many variables I add for that particular clause, because I'm at least, even in these intermediate clauses where I only add one variable, I'm at least making progress. So I'm adding these variables, but I only add basically linearly many of them. So that's one thing you always have to check, that, you know, I could have a really hard problem and reduce it to SAT by first blowing up to something of exponential size, but that wouldn't be okay. And I'll explain in a second why that's the case. The other thing we need to check is that we actually have an equivalent problem. And that's what this sentence is saying, that suppose I had a satisfying assignment to the first one, I need to show that I have a satisfying assignment to the second one, and vice versa. So in this case, you can see that basically, let's just look at this example. If it was true that either x1, not x2, x3, or x4, if one of those was true, then both of these clauses should be satisfied. So let's say x1 was true. Then for the first clause, I can just take x1, and I want to set y1 to what? False. So if I take x1 as true and y1 is false, then I satisfy both of these two clauses, right? This one, x1 covers it. This one, not y1, covers it. That's the role of y1. It's basically just saying, which part of the clause am I going to pay attention to? Same thing holds for these other guys. And you can check that, you know, no matter how many I add, they're basically just logically equivalent, in fact. Right, so the input size, okay, does that make sense that basically we've defined a logically equivalent problem? So that's a key part of these reductions, that I want to show that basically I take an instance of SAT, I convert it into an instance of 3-SAT, and they're basically equivalent. So if the 3-sat version has a satisfying assignment, so does the sat version, and vice versa. And so to make sure that this is a valid reduction, I need the input size to not grow too much. In this case, it grows by at most a factor of 3, and that's because for every literal that appeared in every clause, I make at most a new clause that adds these extra variables into it. So I'm not expanding this by too much. It's just a factor of 3, which is polynomial. The final thing I need to check is that 3-sat is in NP. In this case, that just means, for the same reason that sat was easily verified, 3-sat is easily verified. In fact, it's a special case of sat, so that's easy. Okay, so given all of these ingredients, we can conclude that 3-sat is NP-complete. So let me walk you through basically why we just showed that. So suppose I have some function, let's say I have an algorithm A, which solves 3-sat in poly time. Then I want to conclude that I can solve sat in poly time. And that, in essence, is the reason why we have these extra restrictions. That I can't have the input size grow too much, and 3-sat has to be in NP, and the reduction has to run in polynomial time. The reason is, basically, you could think of this as an actual algorithm. Okay, I take my sat instance, I convert it to a 3-sat instance by adding these dummy variables, and then I feed it into A. And for that whole thing to run in polynomial time, assuming that assuming I have a 3-sat algorithm that runs in polynomial time, or equivalently order 1, it doesn't actually matter. Like, you could assume that you have a magic oracle that does it in constant time. That would be enough. So basically, if you have some magic way to solve 3-sat, I want to show that I can solve sat. But to do that, I can't blow up the problem. If I blew it up to exponential size or something, then even though I could solve 3-sat, I wouldn't necessarily be able to solve sat in polynomial time. So that's the reason for these restrictions. Any questions on this? How many of you have seen this exact reduction before? Is that a question? Okay. Please, more people raise your hands. Have you guys not seen this before? No, okay. Fascinating. Was that a question? No, okay. Okay, so that's sort of, by the way, most of these reductions we'll see today is in a famous paper by Richard Karp from the 70s, who basically took the Cook-Levin theorem and said, hey, there are lots of other NP-complete problems, and you can show that via these simple reductions. And the proofs are very simple. Like, the actual formal proof of this slide is about the same size as the slide. So just to recap what I just said about this formula, so, okay, I switched the roles of A and B. So you know that, some problem is NP-complete, say it's A, and you want to show that some other problem is NP-complete, say B. In this case, A was sat and B was 3-sat. This is the reason, by the way, that the direction of the reduction gets confusing, because you could think about it as trying to solve A, or you could think about it as trying to show that B is hard. And the way you do this is you first show that B is in NP, so at least you can verify it in polynomial time. And then you give a polytime reduction to A. Well, meaning, actually, I guess I should say you're reducing A to B. See, even I screwed it up. So we'll say from A. And the way you do this, like I said, is assume that you could solve B and show that you could solve A. So intuitively, what's happening is you know A is hard. So how do you show that B is hard? Well, you show that if you could solve that, you could solve a hard problem. That's basically the only way we know how to show that something's hard, other than proving the Cook-Levin theorem from scratch. Does that logic make sense? Like, to show that problem B is hard, I can convince you that it's hard by saying, well, if I could solve it, I could solve another hard problem. That's a good way to remember these reductions. So that's what we did here, right? We said, well, I know that this is hard, and I want to show that this is hard. So to show that 3-SAT's hard, I have to be able to convince you that I can solve SAT. Like, wow, SAT's a hard problem. So if you can solve 3-SAT, then that must, 3-SAT must be a hard problem too. Right. So continuing on, we're now going to show that the independent set problem is NP-complete. So what is the independent set problem? We're given a graph, undirected graph, and we want basically intuitively, we want the largest subset of the vertices where there are no edges between them. So they're independent in the sense that there's no link. So no edge between any of the nodes. Formally, we usually write the problem this way, which is not find the largest subset, but just tell me whether there exists a subset that's at least some size k. So in this is called the search version of the problem. So you're just going to output a yes or no. In this case, the input is it's the graph and then a guess. You could think of it that way. And then you just output, yes, there's an independent set of that size or not. So just to make sure you're with me, what's the largest independent set in this graph? Three. Can anyone get 4? So one reason that you know this is NP-complete is that you could be thinking for a long time to convince yourself that there isn't something of size 4. It's a hard problem. That's why it's NP-complete. I'm 99% confident that the answer is 3. Here's 1. But apart from actually coding up something and convincing myself, at least no one's found something of size 4. I'm pretty sure it's 3. Okay, so it's a hard problem, right? And I think if you stare at this and try to come up with a proof that 3 is the max, it's not easy, right? We didn't really do that for the SAT problem, but of course the same is true there. Okay, so our goal, so I want to reduce from 3-SAT. I could reduce from SAT, but 3-SAT's easier, right? 3-SAT has more structure. I can assume that all the clauses have size 3. So it's useful to use 3-SAT. In fact, 3-SAT is a good one to know because probably everything in class that we want to show is NP-complete. You can do it from 3-SAT. Okay, so our goal is to come up with a reduction, which is to say, given some 3-SAT instance, I want to construct a graph and an integer k such that x has an assignment if and only if g has an independent set of size k. That's how to read this statement. So I'm given any Boolean formula in conjunctive normal form where the clauses have size 3 or fewer, and I want to construct some graph and some integer k so that that original formula is satisfiable if and only if that graph has an independent set of size k. If I could do that, and I could construct this in polynomial time, then it would be done. Does that make sense? So I want to construct a version of the independent set problem so that I have this equivalence. And as a corollary, okay, if I could solve independent set, then of course I would just run it on this, and that would tell me the answer here. So if I can solve independent set, then I can solve set, or 3 set. Okay, so this is the task at hand. Construct this graph. This is something that's called a widget. So I don't know why it's called a widget. It's just a thingamajig, I guess. So basically, I want to take a clause and construct something in graph language that's somehow equivalent. In this case, I'm going to create a triangle. So I'm going to have these 3 nodes here, and I'm going to make edges between them. And if you think about this, this is useful because if I'm looking for an independent set, then at most one of these nodes can be in the independent set. So suppose I interpret that as this variable is true, or this literal is true. So maybe I say literal because it could be a negated variable. Let me make these slightly bigger. Okay, so suppose I had x, y, and z. Okay, if the clause was satisfiable, then at least one of them is true, so I should take that node to be in the independent set. I'm just giving you some intuition. And correspondingly, if there's an independent set of the right size, and we'll take the size to be the number of clauses, then I know at least one of these guys is set to true. So that's how it's going to work. Of course, if I had another clause that had a not x in it, maybe I have not x, y, z, I have to make sure that I'm not choosing both of those nodes. That's sort of the tricky part. And to do that, I'm just going to add an edge between them. So that enforces the constraint that if I chose x to be true, I can't choose not x to be true. Okay, I know this is very vague. Here's an example. So let's take this clause, or this is our formula, and I'm just going to construct the graph basically as I hand waved in the last slide. So here I've got not x, not z, and y. So this is the first clause, this is the second clause, third clause, and fourth clause. And in addition, I just add edges between pairs of literals that are opposite in negation. So between z bar and z, between x and x bar. So all I have are triangles and those constraints. And I claim that if there's a, so I think the easy one is, if there's a satisfying assignment, then there's an independent set of size, the number of clauses. Right? Because at least one of these guys, in every clause at least, there's some Boolean assignment to the variables so that there's one true in every clause. And by the only extra edges I've added are between variables and their negations, so I'm not going to have any of those edges, right? If I just take one node that's true in each clause, I will have satisfied that I won't ever choose both y and y bar, right? So if I have a satisfying assignment, I do have an independent set. And the reverse holds basically also because of these edges. So I'm making sure that whatever independent set I choose, I can set those variables or those literals to be true, and I won't conflict between clauses. Just as an example, well, is this clause satisfiable? Is this a formula satisfiable? Yes? So somebody give me some assignment that works here. Y, Z, not X. Sure. Okay. So we're going to say, so I'll just write it this way. So X is false, Y is true, Z is true. Okay. So let's see how this looks. So in the first clause, I could choose either Y or not X for my independent set. So let's just choose one of them, say not X. So that's going to be in the independent set. For the next clause, let's see, I could choose, I only have Z, so I'm forced to choose Z for that guy. Next clause, I could choose Y or Z. Sure, let's choose Z again. And then for the last one, I guess I have to choose not X. Okay. So I never chose a not X and an X, and vice versa. And okay, so that's how to go from an assignment to an independent set. Is that helpful to go through that example? And you can just check, you know, in the clauses where I had multiple options, I could choose any of them. It doesn't matter. Okay, and now if I go backwards, you know, you can just check. It just works the same way. So I just choose an independent set, and because I know that I'm not, you know, violating these constraints, if I have one of size k, where k is the number of clauses, then that corresponds to assignment. If I don't, then that means that there isn't a satisfying assignment, because there's no way to put those nodes in. Okay, the actual proof of this takes a little more care, but I just wanted to give this example. So this isn't the most interesting widget I will give you, but these are called widgets. So you're not constructing any old graph. It has a graph with this particular structure, and this would be called a clause widget. And every once in a while, you have to be kind of clever with how you build these things up. But you could think of this as, hey, I can encode 3set into a graph so that the independent set problem tells me what the satisfying assignment is. So in some sense, NP-complete problems, well, they're all reducible to each other, right? If I have two NP-complete problems, that means, you know, each problem is in NP, and by definition of NP-complete, I can reduce it to the other one. So you can think of these reductions as just encoding one problem into another. And they're just as hard, so if I can solve one, I can solve the other. For those of you who haven't seen this before, is it getting better or worse as we go? Any questions? Yeah.
I don't want to throw off your slide order, but I'd like to see one that the output size does grow like too fast. Or you know what I'm saying? That the output isn't polynomial.
Yeah. Good question.
Is there somewhere I can?
So let me think if I can come up with a really trivial one. Okay, suppose I wanted to reduce SAT to just checking a formula, just checking an assignment. This is not quite what you asked for, but it has the same intuition. So you might say, oh wait, you know, if I can just check an assignment, then maybe I can solve SAT. And here's how I could do it. I could have a reduction that just takes a formula, enumerates all the possible assignments, and checks each one of them. So now if I have an oracle that can just check them, of course we know we can do that in linear time, but you know, if you just assume that that's an NP-complete problem or something, you'll see what but let's just go through this example. So I take a SAT instance, I enumerate all the possible assignments. Hey, I can check each one in polynomial time, so therefore I can solve SAT. And the problem is the number of assignments is exponential. So similarly, I could have a problem that's even harder than NP. There's a whole hierarchy of these problems. And if I tried to reduce an NP-complete problem to that, then I would probably find that the only way I can do that is by having an exponential number of calls to this thing. just like in that assignment case. That's a good question. Did that help? I think so. Okay. Any other questions? All right. Here's a much easier one. So no widgets in this one. Independent set of vertex cover. So what is vertex cover? Again, we're going to find a subset of the vertices, but we want to cover all the edges. So you could think of this as like generators for an electrical network or something like that. I want to cover all the edges, or maybe I'm putting spies and I want to make sure I can see down every road or something. I don't know, whatever. So again, we have a subset of nodes. Now we need to make sure that every node in our set S is touching one of the edges or every edge is touching one of the nodes in S. So again, I can write this as the so-called search problem, which is given a graph and a proposed size k, does there exist a vertex cover of at most k? Why did we go from at least k to at most k?
Sources we're using.
Yeah, because adding more nodes only makes it easier, right? I could just add every node, then I'm done. So I actually want the smallest vertex cover possible, right? So the hard problem is, does there exist a vertex cover of size at most k? And of course, I'm going to ask you what the answer is for this graph again. Well, what's the largest, or what's the smallest vertex cover? Yeah.
5.
5. Oh, good. What's the vertex cover of size 5?
So not the rightmost one, but the one just to the left of it.
This guy?
Yeah.
Okay.
The 2 corners on the left side.
These guys?
Right. And 2 that are just to the right of those corners.
Still missing one.
We're missing these guys. Actually, we're missing a few.
Yeah.
Or no, we have this one, but I guess we're missing those 2. Anything else? I guess we're missing this one. I should be writing X's for those. Okay. Well, it'll be much easier to figure this out after I tell you what the reduction is. But let me just say, hey, here's that independent set from last time. So let's take this as our vertex cover. See, does that work out? So the reason is, well, if you think about it, the complement of an independent set is by definition a vertex cover. Because a vertex cover, all the nodes did not share an edge. So, wait, how does this argument go? Right. So thank you. So if I have the largest independent set, then that would be true. If I added any other node, then I would have already covered that edge. There's a slick like 2-line proof that I've forgotten, but it basically is that. You can just check like every edge. I have to be missing the nodes on the other ends of all the edges from the independent set, and therefore, if I add those nodes, I'm covering that edge. Anyway, sorry I forgot the 2-line proof, but I think visually it's pretty obvious in this example. So it does end up. It is true that independent set. So if S is an independent set, if and only if V minus S is a vertex cover. So therefore, this is the simplest possible reduction, right? I just find an independent set and ask, in particular, hey, is there an independent set of size V minus K? If there is, then there's a vertex cover of size K. Make sense? And it's obviously polynomial time. I don't even have to do anything, basically. I just use the same graph. Okay, so we have now, let's see, sat, 3-sat, independent set, vertex cover. One last one, set cover. I think it's the last one. Yeah. Okay, so here it's just a strictly more general covering problem. So here we have some set, some universe with some elements in it. Say there are n of them, and we have a bunch of subsets that cover, some portion of these: S1, S2, S3. And the problem is, well, I want to cover all the elements with the fewest number of sets possible. This should have been a 2. So it's basically the same as the vertex cover, but more general. And so now the search version of the problem again is, do there exist K or fewer subsets, or just K if you like, covering U? So I kind of hinted what the reduction should be in 2 places. So how do we reduce vertex cover to set cover? How can we show that if we could solve the more general set cover problem, then we can solve vertex cover? Okay, so
this problem here.
Okay,
I'm
sure.
missing something. Is the fewest number of subsets just 1?
In this case, no, right? So I could choose any of these subsets. If I only have one, I'm still missing some elements.
Oh, okay, so you have these subsets. Okay.
Yeah, so you're given these subsets. Right. Yeah, you can't just take U as, you can't make up
Right,
subsets. Yeah, good question. Yeah, so you're given the set of subsets that you're allowed to choose from.
Okay.
And that's what I've
Okay.
drawn here. Yeah, good question. Okay, so we're trying to show that if we could solve set cover, we could solve vertex cover. And to do that, we can follow the usual reduction formula, which is, given an instance of vertex cover, convert it to a set cover problem. Convert it to a set cover instance. So let's start with that. So given some G and K, ... So I'm given the graph on some set of vertices and edges and some integer K, and I want to convert that into a set cover problem. It's not too bad. I think you guys can get this.
You're saying just mechanically, how do we represent the set cover problem as a graph?
Yeah, so just,
Yeah.
right, so give me,
So the elements of the set are nodes, and then
okay, good.
any of your subsets that are given to you create edges between those nodes.
So let's take U equal to V. So the things that we're trying to cover, or sorry, actually U should be E. I don't know if that's what you said.
Yes.
The thing that we're
Yeah.
trying to cover is edges, so U should be E. Does that make sense? The universe of things that we're trying to cover are the edges in the vertex cover problem. Okay. Keep going. So now we just need to specify the S's, right?
Yeah, sorry, I had it and now it's gone.
Can I try a totally different direction?
Sure.
Okay. If you let all the subsets be vertices and you put edges based on inclusion, can you do directed?
Yeah, so I think that is the right idea. So we're going to have one set for each vertex.
And then if one of the sets is completely included in the other set, draw an arrow
What should the sets be, though?
What should what say?
So these should be subsets of U. There is going to be a set for every vertex. That makes sense because in the vertex cover problem, the thing that we could choose is vertices. So we're going to have a subset of edges that corresponds to every vertex. Let's just look at this. Okay, so look at this vertex. What's the set of edges that it covers? Just the set of edges that it covers, right? I mean, so E equals U comma V. I guess, yeah, you can write this different ways, but a subset of edges such that E equals VU for some U. Or, you know, you could also write this as the set of E incident to V, whatever. We all know what we're talking about, right? It's just the set of edges that touch V. And now we're done. Does that make sense? So we're, you know, in a set cover problem, we just have some general universe and general sets. Here we're just saying, oh, actually, the universe that I'm trying to cover are the edges, and the sets correspond to each vertex. In this case, it would be this set would correspond to this vertex. And I have a bunch of these sets. And if I can solve that set cover problem, well, it's exactly the same as the vertex cover problem. So this reduction is also easy because set cover is just strictly more powerful. It'd be similar if we tried to show that SAT was hard if we already knew that 3-SAT was hard. Well, 3-SAT is just a special case of SAT. So that's the same kind of reduction that we're doing here. Vertex cover is just literally a special case of set cover. Give me a graph, and I just write it down immediately. Right, and so the question of whether there exists K subsets covering U just immediately translate to whether there exists K vertices that cover all the edges. Yeah?
Graph.
What do you mean?
Like, are you...
It's just given to you. So you could be given this graph, for example.
Okay.
I'm not sure what you
What
mean.
do the vertices represent in the graph? Do they have any interpretation in terms of the problem that we're looking at for set cover?
No, because we're starting with vertex cover. So, yeah, so like in this example, the graph is representing 3-SAT problem, but not vice versa,
Okay.
if that makes sense. So I took a 3-SAT problem, I converted it into a graph. Here I'm taking a graph, converting it into sets.
Okay.
So the set should have some interpretation in the graph, but not vice versa.
Okay.
Okay, so this stuff takes a while to get used to. The homework has some reductions. Please, if you have any questions about this, I will happily go through the entire office hours going through all of this again. The point of the homework is basically to get you really to think about how this stuff works. So if you have questions at this point as you're doing the homework, please come to office hours. And just to recap, so we've now shown that all of the, well, shown, I've kind of hopefully convinced you, if not rigorously, that SAT, 3-SAT, independent set, vertex cover, and set cover are all NP-complete problems. Of course, there are many, many, many more. There's a compendium of NP-complete problems online, which has thousands and thousands of entries. And by a corollary of the fact that we don't know whether P is equal to NP, we don't know an efficient algorithm for any of these problems. So that's why it's useful to know about NP-complete problems, because if something feels NP-complete as you're trying to solve something in the real world, you know to give up. And that's very important, right? Because at some point you're thinking to yourself, well, I could still try to find an efficient algorithm for this problem, but if I could do that, I would be the most famous mathematician of this century. And it might not happen, so maybe I should just, try to do something else. By all means, go for it, but yeah.
Do you suspect there's some on that list of thousands that are actually not NP-complete, that just haven't been solved yet, or?
So they're all definitely NP-complete,
Okay.
in the sense that they all have a reduction. So if one of them falls, they all fall. That's the nice thing about NP-completeness. So all you need to do is solve any one of them, and then you'll have shown that P equals NP. I see some of you perked up after that. There's $1 million on the line for that, which is not a lot of money these days. They couldn't even buy a house in Boulder. That's not. But okay, so we don't know efficient algorithms for these problems, but sometimes there are fast approximation algorithms. And so what's an approximation algorithm? It means that, say for the vertex cover problem, maybe I found a vertex cover, it's just not as small as it could have been. And I can prove that, okay, it's not too much larger than it needed to be. And often that's good enough in practice. So I conveniently forgot my notes for today, but let's see if I can come up with this proof on the fly. That's always exciting. Okay, so I'm going to show you an approximation algorithm for set cover, I hope. So again, this is set cover. We have this universe and a bunch of predefined subsets, and the question is whether there exist k-subsets covering U. And what we're going to do is we're going to find some subsets such that if there were k, then we don't have much more than k, and it is a valid cover. That would be an approximation. First, let me convince you that the greedy algorithm fails. So what is the greedy algorithm here? What's like the most natural greedy algorithm? Right, so the first set we would choose maybe would be S1. That has 6. Everything else has 5 or fewer. And then maybe after that, we choose the next set that gobbles up the most remaining elements, right? In this case, it's actually tied between S3 and S4. But in any case, we have to take them both. So that would be the output of a greedy algorithm for this case, this particular greedy algorithm. What's actually the optimal set cover here? 2 and 5. So that's why greedy fails. Sometimes the set that has the most at the beginning doesn't make progress towards sort of the optimal solution. There might be a different way of breaking it up that sort of the puzzle pieces fit nicely together. But we're going to show that the greedy algorithm is actually not too bad. So we're going to show that, okay, suppose we have n elements in our ground set, in our universe, and suppose that the optimal solution used k sets, then we're going to show that, well, the greedy algorithm terminates after at most k log n sets. So it's only log n multiplicatively bigger than it needed to be, which in some cases is terrible, but in some cases it's not too bad. Okay. How many of you have heard of the pigeonhole principle? Oh, great. Okay. So, I want to argue that NT, which is the number of elements that I still have left to cover after T steps, is at most 1 minus 1 over k and T minus 1. Which is to say that at every stage of the algorithm, if NT say NT minus 1 are the elements I have left to cover at stage T minus 1, I can find a set that covers at least a 1 over k fraction of them. This follows from the pigeonhole principle. Okay, so suppose I've already covered these elements and I still have these left, right? And suppose k was 3, whatever. What would go wrong if I couldn't find even a single set that covered at least a third of those dots? The argument is, well, okay, I have some set cover that covers everything with only 3 sets, right? So in particular, I have 3 sets that cover all the remaining dots. But if I couldn't find a single set that covered at least a third, then I have a contradiction. Another way to think about it is, okay, I have some set cover. I don't know what it is, but I know it's out there. So at least one of those sets in the set cover, or maybe something else, would cover a third of these elements, right? Because it has to, I have 3 sets that cover everything. How is that? So I claim that, rewriting this in English can always find a set covering 1 over k of remaining elements. Make sense? So that's sort of the hard part. The next part is converting that inequality into something that we can actually use, and that's from this inequality. So every once in a while, I'll throw up a slide like this. You don't really have to memorize these things. I actually never remember these things, but you can always look them up. In this case, e to the minus x is a convex function, so in particular, it has to lie above its gradient. Or you can just take the Taylor expansion. There are lots of ways to actually prove this, or you could just believe this picture. But it is true that e to the minus x is greater than or equal to 1 minus x for all x. Okay, why am I telling you that? Because here's 1 minus x, so I'm going to write this as e to the minus 1 over k and t minus 1. So 1 minus 1 over k is less than or equal to, so this is 1 minus 1 over k and e to the minus 1 over k. Oops. Cool? Really that just makes the math easy because, well, now I can just multiply. Basically, to get from n0 to nt, I have e to the minus t over k times n, right? Which is to say, I mean, every time I choose another set, I'm reducing the number of elements that I need to cover by 1 minus 1 over k, which is less than or equal to e to the minus t over k. So e to the minus 1 over k, but now I can sort of simplify that easily. Okay, we're almost there. Now take capital T, which will be the total number of sets that I actually take, to be k log n. That implies from this that n capital T is less than or equal to 1. Right, I plug this in and I get k log n over k, which simplifies to e to the minus log n, which simplifies to 1 over n, so I cancel the n. So after k log n sets, I now only have one element left to cover. So I just take any set that contains that. Of course, I need to have some set that contains it. So strictly speaking, I guess I should say k log n plus 1 is the number of sets I need. If you do more careful analysis, you don't need that extra one. How is that? Basically what's going on is I'm reducing by some constant factor that depends on k, the number of elements remaining. So of course, after roughly log n, in this case exactly k log n, because that was the factor, I cover everything. Okay, so this is in a sense the simplest kind of approximation algorithm you can get. You just do something kind of myopic and stupid, and in the end it's not too bad. Okay, so let me see, what else did I want to tell you? Oh, okay, we might actually be in good shape. Okay, so next up is vertex cover. So I'm going to show you an approximation algorithm for vertex cover. So this is the problem again. I'm trying to choose a subset of the vertices that touch all the edges. The first thing you might think of is to just use the set cover approximation. So what would be the factor that we get in that case? So for set cover, we said if you have n elements to cover in the optimal solution used k, then you'd get k log n sets. So I'm after this log n factor. What does that translate to here? What was the reduction we had? U was equal to what? E. And the sets, we had some set of the edges that were incident to V. Write it compactly that way. Okay, so what is n then? N is, right, it's the number of edges. So in the worst case, it could be V squared. So we get something like, so if we use set cover, we get if k is the optimal vertex cover, we get something like 2k log V, something like that in the worst case, if you have lots of edges. It turns out you can do a lot better. You can actually get rid of this term, which is pretty nice. It's almost the best that you could hope for, a constant factor. And so let me just quickly show you the algorithm. So what we're going to do is we're going to find some matchings in the graph. And we're going to show that, well, if you have a certain type of matching, then you can bound the size of the vertex cover. So let's first establish these two claims. Do you guys know what a matching is? So matching is a set of edges where no two endpoints are shared. So none of the edges touch each other. That's a matching. You can think of this as like, pairing up to do homework in pairs, right? So that's what a matching is. And I claim first that for any matching, the optimal vertex cover is at least the size of the matching. So the best vertex cover you could do has to at least be the size of this matching for any matching that I find. So let's take this matching. The argument is just, well, I need to at least cover the edges that I checked. I need to at least cover the edges in the matching. And the only way to cover those edges is to take one of the two endpoints of the matching. And by construction, the matching, none of these edges are reused, right? None of the vertices in the matching covers two of them, just by definition. So if I have any matching, I mean, it could just be like these two. It doesn't have to be a good matching. But any matching that I have, I know that I at least need to choose one of the endpoints of those edges to add to my vertex cover. Okay, so need to add one endpoint for each E in the matching. Okay, so that's the lower bound. Now I want to say that, okay, for any maximal matching, the best vertex cover is at most twice the size of that matching. So what do I mean by maximal? A maximal matching is one where I can't add any more edges. Which I think, okay, I need this one. So now I have a maximal matching. I can't add any more edges to the matching. It might not be the maximum matching, which means the highest cardinality, so the best matching I could find that matches as many, I pair up as many people as I can. But it's maximal in that starting from this matching, I can't add another edge. Oh, whoops. Now do I have a maximal matching? Is it good now? Okay. All right. Okay, so if I have a maximal matching, I want to show that the optimal vertex cover is at most twice that size. The proof is very simple. Add U and V to vertex cover for every UV in the matching. Sorry, let me just. So for every edge in the matching, I just add both endpoints to the vertex cover. And I claim that that is a vertex cover. So I have to convince you that I've covered all the edges. So if I have some maximal matching, and I add all the endpoints of the matching, so everyone who is paired up, I can't have missed any edges. Why is that? Suppose I missed an edge. What does that mean? It means that neither endpoint of the edge was already in my vertex cover, right? So if neither endpoint was in the vertex cover, then I could have matched those two guys, right? So if I have two nodes sitting here, and none of the wait, what am I trying to say? Right, none of these vertices were in the matching, were an endpoint of the matching, then that's by definition what it means for me to be able to match that edge. I haven't already matched either of these vertices. They're both free. So they're free to be matched. So if edge left over could have added to M, which is a contradiction. Because M was the maximal matching. Any edge that I could add, I've already added. Might not be the best matching, but at least, if there's just some pair just sitting there, I at least match them up. So this tells us an algorithm, these two claims. I said for any matching that if I just take, since I need to match, I need to cover that edge, the vertex cover has to be at least the size of that matching. And if I take a maximal matching, then the optimal vertex cover is at most twice that size. Here's an algorithm. Find a maximal matching and throw both of the endpoints in to the vertex cover. So compute maximal M, add all matched nodes to vertex cover. And the reason, so I want to convince you that, let's say this solution, let's call it ALG. I want to convince you that the size of the vertex cover returned by the algorithm is at most twice the optimal vertex cover. And I claim it just follows from these two facts. Right, because this is the size of what we found, right? That's how many vertices are in the vertex cover we found. And opt is at least the size of M, so it's at least half of what we found. So right, I can write this, so this is equal to ALG. So this is equal to ALG over 2 for that same M. Because this holds for any matching. So in particular, it holds for the one that we found. So basically, we find a maximal matching, we throw both endpoints in, and we know that we weren't worse than twice as bad because at least the edges that we matched had to be covered. So the optimal solution had to at least cover those edges. So I've only, at most blown up my vertex cover by 2. Let me show you an example. So here's a graph, and here's what happens to be the optimal vertex cover. And here's what the algorithm does. By the way, this is a greedy algorithm because it only has to be a maximal matching. So you can construct it like this. Oh, I found an edge, add both endpoints. Okay, now remove all edges that are incident to those guys, and then just repeat. So I just keep adding edges. I don't have to think hard. Whenever I find an edge, I add them both. So suppose I started with this guy, and then I added this, and then I added this. Then, I don't know, maybe I'll add this edge, then maybe this edge, then this edge. I think that's what they did. Okay. So it could have been anything. Like at this point, I could have chosen that edge. It doesn't matter. Just as long as I keep choosing an edge, in the end, I'll run out of edges that I can add, so it's going to be maximal. It doesn't have to be a good matching, just maximal. And then I just add both of those endpoints into the vertex cover. So in this case, it looks terrible because we've basically chosen all but 4 vertices. But, on a general graph, you can show that you always get at most twice the number that you needed. Yeah?
Find a maximal matching, is it necessary to ensure that all the vertices are connected? I mean, for example, here there are 4 that are not connected, right? So the 4 white ones are not connected to any other.
Right. You just have to wait for the matching.
Yeah, for the maximum matching.
Okay, so if it is right, so I haven't matched all nodes. In this case, if I had matched all nodes, I would have found the maximum matching. Let's see, how can you do that? I guess you would just do these. So that would be a much better matching. So I didn't find that one, but I found one where I'm stuck. I can't add any more. So I can't add an additional match because none of these nodes share an endpoint.
I'm not sure I quite understood the difference between maximum and maximal.
What's the difference?
Yeah, so this comes up a bunch. Maximal means I can't add to the solution to make it better. Maximum means I found the best solution overall. You can think of it, if you're familiar with optimization, you could think of it as like maximum, okay, well, I don't know why I minimized. Okay, let's do maximizing. Maximum would be this one. This would be a maximal solution. There isn't a better one nearby.
Local max.
Yeah, you can think of it as a local max, right? So I can't just add something to it to make it better. So, you know, greedy might wind you up here. Maybe you'd rather be here, but we show that at least if you find a local max, then you're within a factor of 2 of the best. I think that's all I wanted to say. Any questions on this? Okay, so approximation algorithms will come up again. So hopefully this argument of like bounding the optimal and the algorithm makes sense. The last slide I have here is just for fun. You may have heard of the recent result by Laszlo Babai showing that graph isomorphism is now, there's a quasi-polynomial time algorithm. What the heck is quasi-polynomial time? It's a runtime that looks like this. So if C equals 1, then this is just polynomial time. If C is less than 1, then it's sublinear. And if C is greater than 1, then it's quasi-polynomial, but it's still less than exponential. So it's like, it's really slow, but not exponentially slow. So it's not polynomial time, but it's probably not NP-complete. Probably. So this is an interesting problem that sort of sits between P and NP as far as we know. Anyway, next time we'll do minimum spanning trees.